paper will be given by Professor Chuang. Thank you. I'm really great to have this opportunity to come here to discuss with you about my work. I really enjoy the high quality and quantity of food the meeting has provided, and I also enjoy the high quality of the papers which has been presented here, even though I cannot understand all of them because of my limited background. Okay, first of all, I have to acknowledge the co-authors, Mike Galagos, Roger Krismurthy. They have performed experimental work and prepared this set of slides here. Okay, first of all, I'd like to do here is to discuss with you about the relationship between the COH2 reactions, which is CO hydrogenation, and COH2 ethylene reaction, which is also called ethylene hydroformylation reaction. Ethylene hydroformylation reactions. Let's take a look at the relationship between these two reactions. Okay, in carbon monoxide hydrogenations, the CO usually dissociate on the surface of the catalyst to form the surface carbons, then follow the hydrogenation step to form the methyl group here. And usually we put the X here to indicate this species may be a methyl or maybe a methylene species. And this species can further hydrogenate to form the methanes or undergo what is so-called the CO insertions and leading to the formation of the acetaldehyde or ethanols. Okay, there are debate in the literature about whether ethanol is formed through the hydrogenation of acetaldehyde or going through the separate path. In my talk here, I will just focus on the formation of acetaldehyde and formation of the propionaldehyde because the catalyst we have is selected for the formation of aldehyde instead of alcohol. In the second reaction here, which is ethylene hydroformylation reaction, and this reaction has been used as a probe reaction to determine the CO insertion activity of the catalyst. And the use of this reaction can prevent the complication from the CO dissociation steps. And in this step here, the ethylene can be hydrogenated to form the halfly hydrogenous species, which is ethyl. And in fact, I believe nobody ever see this ethyl species before. And this ethyl can be hydrogenated to form the ethane or undergo CO insertion to form the propionaldehyde. So we believe these two CO insertion steps are very similar. And these reaction steps can take place on the surface of metals. Carbon monoxide dissociation, hydrogenation, and chain growth are believed to occur on the metal surface, and some of them occur on the ensemble, which is a group of surface atoms. CO insertion has been shown to occur on a single atom site, and this site can be an ion site or atom site at zero valence state. The CO hydrogenation selectivity and the ethylene hydroformylation selectivity depends on not only the catalyst composition but also on the reaction conditions. For example, this is the work we published around 8 years ago, and we found that increasing in reaction ratio caused a significant increase in the selectivity and the rate of formation for the acetaldehyde and the ethanols. So the objective of this study here is to investigate the effect of pressure on the residence time of intermediates leading to the acetaldehyde and the propionaldehyde. The apparatus we use for this study is here. Here's a schematic of the in situ infrared cell we use. And this cell is developed based on the design of Professor Bell and Professor Ishikawa, and we also refer to the design by the Professor Van Nuys. And finally, we come out with this Ackermann design here. And this design here consists of 4 pieces of flange and hollow stainless cylinders here. And the O-ring here, the bitone O-ring is used here to develop a seal between the glass calcium fluoride window and stainless steels. And inside of this hollow cylinder here, we fill up the hollow cylinder with a calcium fluoride rod, so we can observe primarily the adult species instead of the gas phase species. And this reactor can be operated up to the 460 degrees C and pressure up to the 60 atmosphere based on a design factor of 4. So in fact, we can push this up to 120 atmospheres. And this reactor was placed in the chamber of this FTIR. And I don't want to mention the kind of FTIR we use because we have a bad relationship with this vendor, this manufacturer. So I don't want to do any advertisement about their products. This institute cell, infrared cell is placed in these FTIR spectrometers, and we also designed various lines and bars here to produce step change in the reactant concentration. In this case here, we can produce a step change in C13O concentration, and then we can also produce a pulse change in the C13O concentrations. And the use of infrared spectroscopy allows us to observe how the adult species change, to observe the dynamic of the adult species during the switch. And the use of mass spectrometer here allows us to observe the dynamic of the gas phase product response. And the transient technique has been widely used in the catalysis research. And based on my knowledge, the concept of transient, the use of transient techniques in catalysis was first proposed by Professor Tamaru 30 years ago, and later was developed by the technique was further developed by the Professor Bennett, Peppers, and Bell. And this technique can provide information about the rate constant of elementary steps, surface coverage, and the residence time of the intermediates. And in fact, the most direct information provided by this technique is the average residence time of intermediate leading to the product. In a step transient, what we do here is that we switch. In this case, we're doing the carbon monoxide transient, so we switch C12O to C13O. The purpose of switching C12O to C13O here is to maintain the scaly surface under the steady state condition, because we think the C12O and C13O have the same chemical property. So by replacing the C12O with the C13O, we can maintain the surface under the steady state conditions. And the response here, we can either monitor by the FTIR or the mass spectrometers. In the step transient response, the area above this transient curve is equivalent to the average residence time of intermediate leading to the product. In the post-transient, what we do here is we introduce 10 cc of C13O and to replace another 10 cc of C12O species. And there is an advantage of using the post-transient. As you can see here, post-transient is much cheaper because the isotope species is very expensive, and we can use this post-transient to study the reaction under the high pressure conditions. And step response is a very good, step transient method is a very good method, but it will be extremely expensive to be used to study the reaction under the high pressure conditions. And basically, the step transient and the post-transient provide the similar information. For example, here, the FT is a normalized step response. ET is a normalized pulse response. Based on the theory of the residence time distribution theory in chemical reaction engineering, we know the derivative of the FT with respect to time equal to ET. On the other words, the integration of the pulse response is equal to the step response. So what I'm going to do here is to show you this relationship does hold for the reaction systems. And I'm going to use this technique here to study the effect of the overall pressure, reaction pressure on the residence time of the intermediate leading to the aldehyde. There are three sets of data I want to show you. The first set of data is a steady state result. This is a steady state ethylene hydroformylation reactions. And the reaction was conducted in the in-situ infrared cells, and the product distribution was determined by the gas chromatographers. And as you can see here, the rate of the acetaldehyde formation increased with pressure. And the catalyst we started here is the rhodium silica catalyst. It's a 4% rhodium silica catalyst. Rhodium is prepared by impregnation method using the rhodium chloride precursors. And we can take a look at the table figure here. As you can see, increasing pressure causes significant increase in selectivity for water propionaldehyde. And let's take a look at the steady state infrared results. These two double band here are the PR branch of the carbon monoxide. So as the pressure increase, the gas phase CO band intensity also increase. However, the intensity of the absorbed CO didn't change much. For example, 2033 band is a linear CO band. AA1 is a bridge CO band. As the pressure increase, the linear CO band increased by around 5%. And there are other bands here are attributed to the ethylene, ethane, and some of the adsorbed hydrocarbons. And we do not see, we also see a small amount of propionaldehyde on the surface of the catalyst. Okay. Let's take a look at the post-treating result here. The way we conduct this experiment is here. The first thing we do here is put the catalyst in the reactors and pass the ethylene, carbon monoxide, hydrogen through the reactor. And carbon monoxide is coming with a small amount of argon. Argon is used as tracer to determine the effect of transportation line on the response, on the product response. So we maintain the inlet flow at a steady state conditions. Then at a certain moment, we introduce the C13O. And the amount of C13O introduced is 10 cc. And it was introduced into the system by a gas chromatographer sampling valve. And as you can see, when we introduce the C13O come out, coming down, and C12O coming down and going up. The symmetric nature of these two, of the positive pulse and negative pulse here indicate C12O has been replaced by C13O at a 1-to-1 ratio. So it's important to control it at 1-to-1 ratio so that the catalyst surface won't be disturbed. And Mike Belago and Roger Chris-Murphy has worked very hard to create this result. So we have spent a couple $1,000. Finally, we are able to create this result here. And argon curve is also coming down too. And argon curve here provides the information about the effect of the transportation line and reactor follow-up on the transient response. And here the response of the C13 propionaldehyde. And the average residence time of the intermediate leading to propionaldehyde is determined as 2.8 under these conditions. And let's take a look at the infrared spectrum under this condition. This condition is at 240 degrees C and 1 atmosphere. Okay, 2038 is a C12, linear C12O. 1899 is a C12, it's a bridge C12O. And at a certain moment, this C12O, this adsorbed C12O is replaced by the adsorbed C13O. You know, C13 is heavier than the C12, so it gives a lower vibration frequency. Then again, it was replaced. As you can see, initially we have C12O, then we got a C13O on the surface, then again we have a C12O. The time scale for this switch is exactly the same as the time scale we have observed for this case here. So from this result here, we know there's a rapid exchange between the gaseous CO and adsorbed CO. And we have also conducted step switch experiment on the same catalyst. After we perform this pulse switching experiment, we conduct a step switch experiment. In this step switch experiment, we replace C12O flow by a C13O flow. So C12O coming down, C13O C2H4 coming out, and propanol, C13O propanolaldehyde sodium coming out. The average residence time of intermediate leading to C12O C13 aldehyde is 2.9 minutes. This is the number determined by the step switch. And let's compare the step switch data with the post data. In the post experiment, we found out the tau is around 2.8. Tau is the average residence time of intermediate leading to propanoldehyde. So the number is very close. Then we also take this data here. This point here is a data point we collected from the mass spec. The solid line is the integration of the post response here. So as you can see, the solid lines match well with the dotted points. So this result here clearly indicate post trending is a good technique, and which can be used to determine the average residence time or intermediate leading to the product. And the information obtained by the post trending is essential the same as information obtained from the step trending. So now, we use this post-trending technique to determine the effect of pressure on the propanoldehyde formations. Okay, the upper figure here is the one you just think is a post-response of the propanoldehyde determined at 1 atmosphere. The bottom figure here is the post-response of propanoldehyde determined at 3 atmosphere. The time here is normalized time. We have to normalize the time because the reaction was run at a different pressure with the same flow rate. So we have normalized the time so we can compare it fairly. The way we normalize the time here is to divide it by a pressure factor here. And as you can see here, the increase in reaction pressure caused a decrease in the residence time or intermediate leading to the propanoldehyde. So here, let me summarize the information we have seen here so far. What we have seen is under the reaction conditions, gases, carbon monoxide rapidly exchange with the surface adsorbed CO. And the tau for propanoldehyde decrease with increasing pressures. On the other word, the intrinsic rate constant for CO insertion increase with the pressure. Based on the call below, the average residence time can be considered as a reciprocal of the intrinsic rate constant if we assume the formation of the product is an irreversible step. The formation of the product is an irreversible step. And usually we can see the TOF is equal to the K theta here. Okay, I'm not going to write down here. Okay, the same technique is also used to study the carbon monoxide hydrogenations using the same catalyst. And here is the transient response of the post response of the methanes and C13O during the CO hydrogenation at 1 atmosphere on the same catalyst. And CO hydrogenation at 1 atmosphere over this catalyst produces only methane, does not produce any aldehyde at all. As we increase the pressure up to the 4 atmosphere, we see the aldehyde is formed, and we also see that response of the methane becomes slower. As you can see here, increasing in the pressure causes a decrease, causes an increase in tau methane from 0.14 to 0.54. And increasing in the pressure also caused the formation of the acetaldehyde here. And the residence time of the intermediate leading to acetaldehyde is somewhat small than the residence time of intermediates leading to the methanes. So here let me summarize our observations. Okay, increasing the pressure causes increase in tau methane. Okay, tau methane indicate the average residence time of intermediate leading to methane. So therefore provide a high probability for CO insertion. In addition, increasing the pressure also causes an increase in the CO insertion activity, intrinsic rate constant for CO insertion. So combination of these factors lead to the formation of acetaldehyde at high pressures. And this is all what I have to present here, and I'd like to acknowledge my department always provide generous support to my research, and U.S. Department of Energy Fossil Energy Research Program and Ohio, State of Ohio to provide equipment funds. Thank you very much. I'll be happy to answer any questions you have. Yes.
Steve, one of the issues that you have to be careful about when you look at transients for products such as acetaldehyde or alcohols is that they can absorb on the transfer lines between the reactor and your mass spectrometer. Can you say something about whether the time constant that you observe for acetaldehyde is purely due to the chemistry, or is it convoluted with the desorption process, the chromatographic process in the transfer?
Yes, sure. This is a very important problem. In fact, we spend a lot of time trying to figure it out whether there is any deposition of the acetaldehyde or propenoaldehyde in the line. And usually, after we finish the experiment, we open the line, you can snare the aldehyde. And in fact, the observation we have seen is in fact is a truly chemistry, because under the reaction condition, in fact, there are a lot of aldehyde absorbed on the surface. And when we perform this switch, the peak here doesn't switch. If we perform a pulse switch, and this peak doesn't switch, and this peak is aldehyde. So this indicates some of aldehydes sit on the surface of the support, and it didn't come off. So we do it very carefully. All the sampling line, all the lines were heated up to 100 degrees by the heating pads. So we try to prevent the absorption of the aldehydes. And we also think, in fact, we have started the reaction under the different partial pressure, and we do see the change in the reaction time of intermediates. So from the heating the lines and also the result we observed, we believe we observe the true chemistry instead of the slow dissolve or freeze dissolve species on the surface of the stainless steel. Yeah, there's an issue we are very concerned about. In fact, my students were more concerned than I am when they perform this experiment. We want to make sure they get the right data. Yes.
But estimation of the activity and
the activation energy of it, yes. We have data for activation energy. The propenoaldehyde, the activation energy for the C2H4 we got in varying levels of 122 kilocalories per mole. Yeah, and for SU-type formulations, the activation energy for propenoaldehyde formulation is around 12 kilocalories per mole. Yes, and for FN formulation is around 16 to 18, it's higher. So we believe those data are true, intrinsic